Good afternoon. Today we're going to be talking about section 3.11, related rates. And this is really our first introduction into using calculus. So what we've been doing is teaching you calculus, and now that you have the basic tools, it's time to use them and apply them to real-world problems. So let's get started with an example. Here's just a teaser question. An oil rig springs a leak, and the oil spreads in a roughly circular path around the rig. If the radius of the oil patch increases at a known rate, can we calculate how quickly the area of the patch is changing? And the answer is yes, even though that was kind of a spoiler. So yes, we certainly can, and we do this through using calculus. So let's look at the full example and I'll explain as we go. So an oil rig springs a leak in calm seas and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? So what we've done here, off to the right, is we've drawn a picture of a circle that's being expanded as our radius is increasing. And that's going to be pretty fundamental. So we've sketched a picture, and that's our first step. In this example, two variables are changing at the same time, the radius and the area of the circle. And you can kind of see that as radius increases, you expect your area to increase too. So they're related, which is why we call it related rates. Luckily, we've got an equation that relates the two. A equals pi r squared. So area equals pi times the radius squared. And we know that both the area and radius are changing as time goes on, so we rewrite the above expression as area as a function of time equals pi times r as a function of time, quantity squared. And our goal is to find a prime of t given r prime of t equals 30 meters per hour. So we take our equation and we differentiate it with respect to time, remembering to use the chain rule. So our equation becomes a prime of t equals 2 pi r of t times r prime of t. And we're interested in a prime of t when r of t equals 100 meters and r prime of t equals 30 meters per hour. So we plug and chug those values in. A prime of t equals 2 pi times 100 meters times 30 meters per hour. And we get 6,000 pi meters squared per hour. So now we're going to do a sanity check, and this is probably one of the most important steps you can take. Area, we know, is measured in meters squared, and we're interested in the time rate of change of the area. So our final units should be in meters squared per that time rate of change of hours. So when we check back in the answer we provided, we know that our units are indeed meters squared per hour. And so we can believe that our answer is a good fit. And when we think about the scale of this problem, 100 meters being the current radius, and the radius increasing at a rate of 30 meters per hour, we can kind of assume that the answer we get should be pretty large. So we do get an answer that's pretty large. So that's another little sanity check that we can do. So let's talk about procedure. So when you have problems like this, the first step you should do is make a sketch of your problem, whether it's just a rough outline of a circle with the radius line and showing that it's increasing, or if you actually draw an oil rig and the ocean and everything like that. Whatever you do, as long as you make a sketch to help you understand the geometry, you're doing the right thing. The next thing you're going to do is write down all the relevant equations for this problem. So in our first example, we had area equals pi r squared. And so we had area and its relationship to radius. Our next step is going to be differentiation of the appropriate equations with respect to time. Now, I say equations plural because in some of these problems, you're going to need to relate multiple equations together to one another before you can move forward. But sometimes you only need one equation. After you differentiate, your next step is going to be substituting in your known values and solving for the desired quantity. And this is going to be your easiest step to take. It's just plugging in values and chugging out the perfect response. So you can put this in a calculator, get out an answer, there you go. And then step 5 is certainly optional, but it's definitely going to be the most helpful just in case you make a mistake. And we use it a lot in engineering, it's done a lot in physics, and not so much in mathematics, but in this section particularly, it is done a lot, and that's sanity check your units. Just like we did at the end, we wanted to see that area, the time rate of change of area is in meters squared per hour, so our answer should be in meters squared per hour. And that's how you do a sanity check. So let's take this procedure and apply it to the next example. Here we have coffee draining out of a conical filter at a rate of 2.25 inches cubed per minute. If the cone is 5 inches tall and has a radius of 2 inches, how fast is the coffee level dropping when the coffee is 3 inches deep? So this seems like a pretty crazy problem, but over here on the right, we've drawn what's going on. We've got our coffee filter. We know that it's a cone shape and that coffee is draining out of it, so it's probably oriented like this with the tip of it pointing down. We know that it's 5 inches tall, and at the top or the base of it, the radius is 2 inches. And we've drawn here the height of the coffee being h of t and the radius of the coffee while it's draining out being r of t. And we know that we can relate volume, radius, and height together by volume equals 1/3 pi r squared times h. So we're going to keep that equation handy for our next set. So step one, we've completed. We've drawn a picture and we've written down an appropriate equation that helps us relate all of our known quantities together. So the next step comes like so. We're interested in the change in height, dh dt, when the height is 3 inches. And we know the change in volume, dv dt. Using similar triangles, we see that the ratio of the radius to the height of the coffee cone is 2/5 at all times. That is, the radius divided by the height is always going to equal 2/5, or r equals 2/5 times h. So now we've got a second equation. We've got volume equals 1/3 pi r squared h, and we've got r equals 2/5 h. So what we're going to do is we're going to substitute in our relationship for r into our original equation. So we're going to sub in 2/5 h into r squared, and we get that volume is equal to 4 pi over 75 h cubed. Now we can differentiate with respect to time. So we get dv dt equals 12 pi over 75 h of t squared times h prime of t. And we can substitute in our known values. So we know that coffee is draining out, so we better have a negative sign. So we have negative 2.25 inches cubed per minute equals 12 pi over 75, 3 inches squared times h prime of t. And we're searching for h prime of t, so our next step is going to be to solve. H prime of t is negative 0.497 inches per minute. And for our sanity check, we're interested in the rate of change of the height with respect to time. So we expect our units to be in inches per minute. And we know the height is decreasing as coffee drains out of our filter. So we know there ought to be a negative sign. So we've got a negative sign and we've got the proper units. Our answer is probably correct. Now, you might be wondering, how did I know to bring in that second equation and use similar triangles? And I say this next part with take it with a grain of salt. When I look at my expression, v equals 1/3 pi r squared h, and I want to take the derivative of this, if I take my derivative of this quantity just as it is, I'm going to end up having to use the product rule and having to know something about the time rate of change of the radius. But I don't know anything about the time rate of change of the radius, and I'm not trying to solve for it. So I want to develop a relationship between r and h so that I'm only dealing with h's. And that's where we get our similar triangles from. And we get that from here. Let me change my color really quick. Everywhere we go, we've got a triangle that looks like this, where our height is 5 inches and our radius is 2 inches. And even as the radius decreases and the height decreases, we're still going to have the ratio of r to h be 2/5. So that's where I go ahead and use my similar triangles. And that's kind of why I bring those in. So that's it for me.